University of Tokyo. So are you online? Are you?
Yes, can you hear me?
Yes, I can hear you. And would you please share your screen?
Okay.
Great, we can see it. So please go ahead.
Okay. Okay. Thank you for the organizers for inviting me. I'm Yu Niino from the University of Tokyo. Today I'd like to talk about our search for simultaneous optical emission from a repeating FRB source using our high-speed camera Tomo-e Gozen. This work is done with the help of collaborators listed here, including both optical and radio observers and also theoreticians. Let me start with talking about the motivation of optical observation of radio source. As we have experienced in the history of astronomy, the finding of the other wavelengths or maybe other messenger habitats parts of transients can revolutionize our understanding of the source, as in the case of the discovery of afterglows and associated supernovae for GR gamma bursts, and more recently the discovery of kilonovae and gamma bursts associated with gravitational wave source also dramatically improved our understanding of those astrophysical events. So we hope to make this kind of breakthrough happen for the understanding of fast radio bursts, and conduct observation of fast radio bursts in other wavelengths than radio. So one way to find FRB counterpart is follow-up observations. Actually, follow-up observations of FRBs are conducted in various wavelengths and also in various timescale or delay times. Unfortunately, there is not yet robust association. There are some candidates, but not very robust. In terms of optical follow-up observations, in some case, association of bright transients are ruled out, such as superluminal supernovae or GRB-associated supernovae. However, the current optical limits in the follow-up observations do not rule out a faint population of transients, such as type 2 supernovae or kilonovae are not ruled out yet, so there are still some discovery space in this line of study. But in this talk, I would like to put more focus on the simultaneous observation rather than follow-ups. About the follow-up studies of FRBs, there will be Tendoko's talk in this afternoon, so I think you can hear more from that talk. Another possible strategy of finding FRB counterpart in other wavelengths or messenger is simultaneous observations. It is not known whether FRBs, the bursts, emit energy in other wavelengths. However, there are some sources known to produce such simultaneous observation. One case, one is pulsars. It is also historically long known source of short radio pulse emission. In some pulsars produce optical or X-ray and also wavelength pulse simultaneously with their radio pulses. This is the upper right panel shows the phase averaged spectra of cloud pulsar time, and actually the optical pulse of from clock pulse is as bright as its radio pulse in terms of flux density, fluence density, I mean. And there's also a case of FRB 2020 or 25A that is FRB like burst from a galactic magnet. In the case of this magnetic burst, X-ray flare was also observed simultaneously with radio burst. Although the relation of this magnetic burst to the extragalactic population of FRBs is still a matter of debate in my understanding, but this is a good example of, that shows other wavelength simultaneous emission is possible for FRB-like event. Besides these empirical observational examples, there are also some theoretical predictions that expect the simultaneous emission from FRBs in other wavelengths. In Yang et al. 2019, they showed the inverse Compton emission in a partial magnetic sphere like environment from the FRB emission can produce optical burst in a simultaneous scale. And sorry if I don't pronounce correctly, 2020 showed that the burst wave, collision of a burst wave into a hot wind bubble can produce optical burst in a second time scale, in a time scale of a second simultaneously with FRB emission. So when we try to catch the simultaneous emission produced by the radio burst, simultaneously with the radio burst, our approach is to do high time resolution observations because at least the radio emission from the FRBs are made in a very short time scale, so that at least the time scale of the phenomena is short, so other wavelengths counterparts can be also short. Although in some theoretical models, the longer time scale of emission is also expected. But in the case of short duration emission, the observation with higher time resolution can achieve better fluence sensitivity because the fluence limit, the minimum fluence the observation can detect is a product of the time averaged flux density limit times the time scale of observation. And in many cases of especially optical observations, the flux density limit is proportional to the minimum flux density detectable is proportional to the observing time the power of minus 0.5. That's why we usually want to observe longer, expose longer for fainter event. But in the case of very short transient, the fluence limit is the product of flux density times, and so in total the detection limit becomes shallower as we observe longer. So this is why we want to use a high-speed instrument. And in this talk, I focus on mainly focus on the observation with short time scale. But there are some, of course, the observing time is not the single parameter that determines the observation sensitivity, and there are some successful cases of observations with longer time scales. And I think soon after this talk, Daiichi Hiromasu's talk will show you some successful cases of this longer exposure time. So in terms of high time resolution simultaneous observation, there are some there have been some studies. In the previous studies have been mainly targeted FRB 12, 11, or 2, that is first discovered repeaters. And in 2017, Harry et al. Was the modeling observation using the ultraspec mounted on Thai National Telescope with putting 0.33 Mijansky limit with a time scale 17 milliseconds using the instrument camera using EMCCD. And there have been also observation using the Cherenkov gamma ray telescope as an optical facility, and in 2018, Magic Collaboration reported the 8.6 Mijansky millisecond frequency limit using their photomultiplier that is designed to detect Cherenkov light. And there have been also simultaneous search for non-repeaters like deeper void Foster, but the optical component was not didn't have very high time resolution and sufficient detection limit for very short flashes. So to increase the number of increase the cases of high-speed optical observations, we use our instrument, the Tomo-e Gozen CMOS camera mounted on the 1.05 meter Schmidt telescope. The Tomo-e Gozen is the name of the camera system shown here, which has which covers the 9-degree diameter field of view of the Schmidt telescope shown here, and it uses 84 CMOS sensors. In total, it covers 20 square degrees field of view, and each sensor has 2,000 times 1,000 pixels, so it can take image in a very fast frame rate of 2 FPS when we read out full of the sensor. But if we read out only a part of the sensor, the frames can be larger, as we expected. And this telescope and camera system is operated by automated Q system, and we usually observe or study finding new young supernovae or asteroids that traveling near close to the Earth, and there are also automatically triggered follow-up system connected with divergent alerting for gravitational waves, and there are also follow-up systems used for the GRVs, and Maxi detected X-ray planets are also under development, and there are also other science cases including FRBs. Using the Tomo-e Gozen camera, we have conducted simultaneous observation with FAST telescope on August 4, 6, 14, and 16 in 2020, and we have used 24.4 frames per second high-speed observation with partial readout. When we read out full image from each sensor, the maximum frame rate is 2 FPS, but reading out only 8 times 5 square arcmeter, we could achieve this frame rate. That is 40.9 milliseconds per frame exposures. And the excellent thing is that the time gap between frames, the gap between each 40.9 millisecond frame is just 0.1 millisecond. So basically, we don't need to worry about losing a burst between the time gap between frames. And observing past band of the Tomo-e Gozen is unfiltered and determined by the sensor sensitivity that is about 3,700 to 7,300 angstrom. The target of this simultaneous observation is FRB 2019 or Y20B, which are just introduced by D, which has very large excess from the Markov relation with the dispersion measure of 1200, but with low redshift. And this source is associated with a compact radio source and that produces many pores, suggesting a very young source. So during the simultaneous observations, 11 bursts are detected, and 6 bursts on August 6, 5 bursts on August 14, but no burst on August 4 and 16th. And the fluence range of the detected burst during the simultaneous observation was 60 to 300 millijansky. There are some dynamic spectra of detected bursts here during the simultaneous observation, and as you can see, the spectra and light curve of the detected burst varies case by case. So in the optical observation by Tomo-e Gozen, no persistent source was detected in the stacked image of the quickly read out movie data, and we extract the light curve of the FRB source position by forced photometry, although we don't detect any source in the stacked image, and we didn't find any optical burst about the noise. This is a light curve extracted from the 4 days of observations, and vertical dashed lines indicate the arrival time of 11 radio bursts that is collected for the solar system Valley Center. This is a close-up view of the burst arrival times, and there is no significant excess around the radio burst arrival before and within 1 second, as shown here. So we conclude there was no optical burst detectable during this observation. Based on the non-detections, we put upper limit on the optical fluence in each optical image that corresponds to the radio burst arrival times. So the limits obtained for each optical frame is shown in sky blue here. The 2 data points are connected, and the lower one is uncorrected for the Milky Way extinction. And we know the FRB source is extragalactic, so we should consider the extinction corrected limits, that is the field symbols on the upper side, and limits obtained in individual images or individual burst is about 0.07 to 0.015 Jansky millisecond. After stacking 11 images that correspond to the radio arrival times, achieve the limit of extinction corrected upper limit of 0.03 Jansky milliseconds that is shown in the bottom of this figure, compared to the previous observations by Ultraspec and Magic. Although our telescope is smaller than theirs, the fluence limit is significantly improved. In order to constrain the nature of FRBs or emission mechanism of the source, it is also important to put the SED limit rather than fluence limits that is obtained by dividing the optical fluence limit by the radio fluence that is detected by the radio telescope. Unfortunately, the radio burst detected during the simultaneous observation had the fluence of 300 millijansky millisecond at most. That is not so very bright radio.
So 5 minutes left.
Okay, thank you. So the limit obtained this time was not so limit on SED obtained this time was not so deeper than the Clark pulsar. There are some other optically detected pulsars that have fainter optical emissions than Clark, so we didn't reach that level of SED limit. But our fluence limit is quite nice. So if we put the similar optical limits simultaneously with brighter bursts, for example, 1 Jansky millisecond or possibly 100 Jansky millisecond, we can get much deeper SED limit that can reach Geminger or possibly interpolated SED of FRB 2004 28A. So detecting, observing simultaneously observing a bright burst is essential. So for that purpose, we need more observation. And to make that realize, we are conducting more observation using a new instrument named TRIX that is mounted on a 3.8 meter telescope in Okayama. This camera can take images in almost 100 FPS and also 3 filter patterns at once. This is an example of the obtained data during the observation of FRB 2020 and 24A in March last year. With finer time sampling than Tomo-e Gozen observations, each frame reaches the 5 sigma limit of 0.03 Jansky millisecond with an exposed time of 10 milliseconds and under good condition. Also, the limit becomes shallower when a cloud passes the gray shade indicates, and more observations of many repeaters and the data analysis are ongoing, so please stay tuned. Besides monitoring of repeaters, we are also conducting radio optical simultaneous observation of non-repeaters. As I mentioned in the introduction, our Tomo-e Gozen camera and Schmidt telescope system has wide field of view of 20 square degrees. So we use that camera to monitor the field of view of China, which has 250 square degrees of the field of view. Although the shape of the field of view of these instruments are quite different, and we cannot overlay them significantly, but the overlapped field of view reaches the 5 square degrees. So we can expect a burst occurring, non-repeating blank field survey for non-repeating burst can catch an event in the overlap field of view at a rate of 1 per 240 hours. More than 50 hours of observations have been conducted so far. No event yet, but that is expected, and further observations are ongoing. So also please stay tuned for this survey. Okay, this is a summary, and the optical counterpart of FRB is not robustly found to date, but many of the studies are ongoing, and we have conducted those speed monitoring about FRB 2019, 2019-0520B, and obtain a deep fluence limit. Further observations are ongoing, and to try to put a more significant constraint on the FRB SED in a wide wavelength range. Thank you.
Great. Thanks you for a really interesting overview for the optical follow-up. Are there any questions from our on-site audience?
Thank you very much for the talk. I'm wondering, how do you determine the target of observing the optical counterparts? Like, do you have any preference or any selection criteria of the host galaxy properties or any properties of the FRBs?
Usually, for the repeating sources, we usually select the sources in active phase when we can observe.
Okay.
If there is a very nearby source or frequent bright burst, that is great. But the primary selection criteria is activity at the time of the observation, currently.
Thank you very much.
Okay. Any questions from online? Do we have any questions?
Question from Yu Niino.
Yeah, can you hear me?
Yes.
Yeah, so yeah, thanks for the interesting talk. So you mentioned, in the case of Tomo-e Gozen, it's 40 milliseconds per frame, and with Seimei, you can go down to 10 milliseconds per frame. Ideally, you might want to go even shorter, but is it difficult to do that with CCD type detectors, or?
Well, with CCD type detectors, the problem is read-out time. CCD sensors uses a couple of seconds to read out the image from sensor. So if you integrate very short time with CCD, the duty cycle of observing will be very short, and you will most likely lose events between the time gap.
I see.
Events.
So to go even shorter, you probably need different types of detectors.
Yes, we need detectors with very short read time, as we did with CMOS sensors to do
Okay.
the high level resolution.
I meant with CMOS detectors, but I mean, if I understood correctly, with Seimei you get down to 10 milliseconds, but it's not.
Yes, with partial readout mode, Seimei can go faster actually, but that makes the field of view quite small, and the telescope tracking of the Seimei telescope is not so excellent. So we might worry about losing the source out of the field of view, but we can try.
I see. Okay, thank you.
Okay, thanks for the great discussion. So I think we can talk later during the discussion section, and let's move to the next talk.